Good morning and welcome back to GeotherMOOC, the free open online course on the geothermal energy value chain, organized by Saipem and the University of Urbino.
Organizzato da Saipem e dall'Università di Urbino.
This is the 7th lesson. As we have progressed along the geothermal value chain, we have now reached the topic of closed-loop geothermal systems. Today's speakers are Gioia Falcone, Director of the Glasgow Centre for Sustainable Energy at the University of Glasgow, and Michele Carpita, Flow Assurance and Process Engineering Lead at Saipem. The session will be structured as follows. Professor Falcone will first introduce closed-loop systems concepts. Michele Carpita will then discuss the optimization of closed-loop systems.
Per poi lasciare la parola a Michele Carpita che parlerà invece dell'ottimizzazione dei sistemi a circuito chiuso.
At this point, I would like to welcome Gioia and Michele and thank them for agreeing to participate and teach this lesson. Michele, I'll place you in the waiting room while Gioia Falcone takes the floor. As mentioned, Gioia Falcone is director of the Glasgow Centre for Sustainable Energy at the University of Glasgow, and she will introduce the closed-loop systems concepts. Gioia, the floor is yours. Thank you, Alessandro. Good morning, everyone, and welcome back. Today, we will discuss the differences between open-loop and closed-loop geothermal systems.
Oggi parleremo della differenza tra i sistemi geotermici a circuito aperto e quelli a circuito chiuso.
On the slide we have already seen, you can find a diagram summarizing open-loop systems on the right, closed-loop systems on the left, and a slightly specialized case known as Advanced Geothermal Systems, or AGS, shown on the far right.
Un caso un pochino particolare di quelli che chiamiamo i sistemi geotermici avanzati, AGS, sull'estrema destra del lucido.
What is the difference? In open-loop systems, the geofluid itself is circulated through the wells. For example, we drill into an aquifer, bringing the water to the surface, extracting its heat, and then re-injecting the same fluid underground.
E poi reiniettamo lo stesso fluido sempre nel sottosuolo dopo aver estratto il calore.
Another example of an open-loop system is the Enhanced Geothermal System, or EGS, where, even if there isn't any water naturally present in the subsurface, water is injected into artificially fractured rock, circulated, and then recovered through a production well. In completely closed-loop systems, however, if we move to the left of the diagram on this slide, we see that historically they were built at shallow depths, generally around 100 to 300 meters. Closed-loop means that we insert a pipe and circulate a clean fluid from the surface inside this pipe without it ever coming into contact with the porous medium or an aquifer. This closed-loop system ensures that the naturally occurring heat in the subsurface is transferred to the circulating fluid, which then carries it to the surface heat that can be used, for example, in combination with a heat pump. These closed-loop systems, originally developed for shallow depths, have since been extended to greater depths, such as 2,000 meters or even deeper. We will look at some case studies in the next few slides. In the example you see on the far right, these deeper closed-loop systems have evolved into quite complex geometries, such as U-shaped pipes or even branching configurations, what I call fork-shaped. So, today we'll look briefly at the differences in heat recovery that can be achieved with these closed systems compared to open ones. And my colleague Michele will also expand on the modeling of these systems. I will give you a few case study examples. So,
Come funziona
how does the
il
simplest
sistema più
closed-loop
semplice che possiamo
system we can
concepire a
conceive
circuito
actually
chiuso?
work? Let's
Immaginiamo un tubo
imagine a
sicuramente
purely
verticale
vertical
per
well
mantenere le
to
cose
keep
molto
things as
semplici
simple as possible
e
and
anche
also to
per
minimize
minimizzare i costi
production
di
costs,
produzione, di cui
as you have
ormai
already
avete anche
learned.
imparato
That is
nella
the
parte
fundamental
fondamentale.
starting point.
Quindi partendo da questo pozzo
Beginning with this
verticale,
vertical
se io
well,
immagino
suppose
di
we insert a
inserire un tubo
concentric pipe into
concentrico
it
nel
and
pozzo
allow a clean
verticale e di
fluid from
far
the
fluire
surface to
in questo
circulate through
sistema
the
un
system.
fluido
How does the
pulito
heat
preso dalla
exchange take
superficie,
place in this
come
case?
funziona lo scambio di calore?
So,
Allora, in
in this
questo
diagram
diagramma
on
a
the left,
sinistra vedete
you
la
see the
configurazione che ho
configuration I
chiamato
called
CXA.
CXA.
È un
It's a
coaxiale, quindi
coaxial
un sistema
system, so
concentrico
a
dove crea un
concentric
tubo
system
nel
in
tubo
which the fluid
e
flows
in
in
cui
the annular
faccio
space
fluire
between
il
the
flusso
outer
di
pipe and
superficie
the
nella
inner pipe.
parte anulare
Then,
tra il
after
tubo
this
esterno e il
fluid,
tubo interno
going down to
e
depth,
poi dopo che
has
questo
recovered the
fluido
heat
andando giù in
naturally
profondità
present
ha
in the
recuperato il
subsoil,
calore
I let it
naturalmente
return
presente
inside the
nel
central
sottosuolo,
pipe
lo faccio
and rise
rivenire
through this central
all'interno
pipe.
del tubo centrale e far risalire il fluido in questo tubo centrale.
For the
Affinché
heat exchange to be
lo
efficient,
scambio di
I
calore sia
must ensure
efficiente, devo
thermal
assicurare
insulation
un
of the central pipe.
isolamento termico
Otherwise,
del
all the
tubo
heat
centrale,
I have
altrimenti tutto il
acquired from the
calore che avrò
surrounding
acquisito
rock would be
dalla
lost
roccia
again to the
circostante
external environment.
verrebbe perso di nuovo con l'ambiente esterno.
In the
Nella configurazione
configuration you
che
see
vedete
on the
sulla
right,
destra
nothing
nulla
changes.
cambia in
In
realtà,
reality,
cambia
the direction
semplicemente
of
la
circulation of the
direzione di
fluid
circolazione del
simply
fluido.
changes.
Lo faccio
I let it
scendere nel tubo
descend into the
centrale e lo
central pipe
faccio
and let it
risalire nella parte
rise in
anulare.
the annular part.
Entrambe le configurazioni,
Both
quelle che
configurations,
chiamiamo
the
A e
ones we
B in
call
questo
A
diagramma,
and
sono
B in
possibili,
this
sono state
diagram, are
testate.
possible and have
Quale
been
è
tested.
la
The
soluzione
optimal
ottimale
solution will
dipenderà dalla
depend on the
profondità di
depth of
implementazione, dai
implementation, the
diametri dei
diameters of the
tubi
various
e dal
pipes, and the
gradiente
geothermal gradient
geotermico
on
in
site.
loco. Normalmente
Normally,
un tubo
however, we
tendiamo a
tend to
usare la
use
configurazione
configuration
A.
A.
Infine, sulla
Finally, on the
destra, il
right,
diagramma che
the
ho chiamato
diagram I've
C
called
è
C
una
is a
visione
top-down
top-down,
view,
quindi una
a
visione
horizontal view
orizzontale
of
di
all the
tutti i
materials found in
materiali
the
che si
well in a
trovano
system of
nel
this type.
pozzo in un sistema di questo
If you
tipo.
start from
Se
the
partite dalla
most
parte più
central part,
centrale, dove c'è
where it
scritto
says
TPO,
TPO,
quello
that
è
is the
il
center
centro
of
del
the
tubo
central pipe
centrale,
where the fluid rises
dove
in
nella
this
configurazione
configuration.
A il fluido
Then,
risale.
outside, the
Poi al
first
di fuori
external
il
layer
primo
is the
strato
annular
esterno è
layer.
lo strato anulare.
Then we have the
Poi
pipe
abbiamo
material
il
that is
materiale
in
del
contact with the
tubo che è a
cement,
contatto
which
con
in
il
turn is
cemento,
in
che a sua
contact with
volta
the
è a contatto
rock.
con la roccia.
You
Avete
learnt
imparato
in the
nella parte di
drilling
drilling
section
come si fa la
how to drill
perforazione in
concentrically,
modo
and you also
concentrico
learnt that
e
once
avete
the
imparato
rock is
anche che una volta
perforated,
perforata la roccia si
pipes
mettono
are
dentro dei
inserted
tubi, per
inside,
esempio
for
metallo,
example, metal
e
pipes.
questi tubi in
In many
molti casi
cases,
devono
these
essere
pipes
cementati,
must be
quindi tra la roccia e
cemented,
il tubo c'è uno
so
strato di
between the
cemento
rock and the
inserito
pipe there
appositamente
is
per
a layer of
assicurare
cement
l'integrità del sistema
inserted
dentro.
specifically to
Quindi
ensure
questo
the
in breve la
long-term
presentazione di quello
integrity
che
of the
chiamiamo
system.
uno
So this,
scambiatore
in
di
short,
calore
is the
profondo in
presentation of
pozzo,
what we call a deep well heat
DBHE. Queste
exchanger,
luci
or
sta per Deep
DBHE.
Borehole Heat Exchanger in
These
inglese,
slides
quindi
refer to
appunto
deep
scambiatore di
borehole
calore in
heat
pozzo
exchanger.
profondo.
These
Questi
systems are
sistemi poi
coupled on the
vengono
surface with
accoppiati in
different
superficie
operating
con
modes.
modalità di
For
utilizzo. Per
example,
esempio, una
once
volta
the
che
heated
il flusso
pump
di
returns
scaldato
to the
ritorna in
surface,
superficie, lo posso
I can
combinare con
combine
una
it
pompa
with a
di
heat
calore
pump that
che a sua
will,
volta
in
sarà
turn, be
connessa con
connected
i
to
frisci,
buildings
con
or
le
houses
case
that I want to
che voglio
heat
andare
or
a
cool.
riscaldare o raffreddare.
This coupling, this
Questo
combination with the
accoppiamento
surface
questa
systems
combinazione con
must be
i
optimized,
sistemi di
so the
superficie
engineering part
va
does not
ottimizzato,
stop at
quindi
bringing the
la
flow to
parte
the surface,
ingegneristica non si ferma
but
a
must
portare il
extend to
flusso in
verifying
superficie, ma deve
compatibility
essere
with the
estesa
temperatures
fino
required at the
alla
end point of
verifica della
use.
compatibilità con le temperature richieste al punto finale di utilizzo. Se
If I want to
voglio
combine this
combinare questo
system with
sistema
houses,
con delle
I must
case,
ensure that
devo
the desired
assicurarmi che
temperature
la
in winter
temperatura
and the
voluta
desired
in
temperature
inverno,
in
la
summer
temperatura voluta
are
in
compatible with the
estate
temperature
siano
returned
compatibili
to
con la
the surface
temperatura
by the well.
riportata in superficie dal pozzo.
This
Questa
table provides
tabella
a
vi
summary of the
riporta
projects
un
that have already been
sommario
completed
dei
around the world
progetti che
using
sono
deep
stati già
borehole heat
eseguiti
exchange.
nel mondo in modalità Deep Borehole Heat Exchanger.
As you can see, these are systems that already exist. So the good news is that we are not talking about science fiction, but about solutions that are already possible and already tested in various countries. There are many examples in China where there has been a lot of activity in this field, and they are all primarily heat applications. This means they are not generating electrical power, but simply producing heat for use in heated environments. Another thing I wanted to point out in this table is the depths reached. Generally, we're talking about depths between 1,200 and 2,800 meters. However, there have also been pilot projects that have reached greater depths. A striking example is the well currently active here in England, in the UK, where I'm speaking to you, at Eden in Cornwall. A well that was originally planned as an EGS was at least temporarily converted into a deep borehole heat exchanger, and this occurred in 2023. This concentric well reaches a depth of more than 5,000 meters. The internal pipe was set at a depth of 3,800 meters, and this well is already producing heat with a connection to the surface. Another example, another case study, is the last pilot project in this table, which I will discuss in more detail in future slides. This latest project is also here in the UK. Speaking of case studies, I'll present two to you today. One is the case study of a well that was drilled in Switzerland with the hope of finding a classic geothermal source of hydrothermal nature. They originally wanted to develop an open loop project, but once they drilled the well, they discovered that the conditions were not optimal at all for an open system. There was not enough permeability, and there was not enough porosity. Rather than throw in the towel, the operators decided to convert that well into a closed-loop well, a deep borehole exchanger. And this project has clearly been successful. It's been in operation since 1996. The well reaches a depth of just over 1,200 meters, and the heat produced, which reaches the surface at not so high temperatures, around 15 degrees Celsius, is used to provide initial heat to the heat pumps located in the local resort hotel called Hof Weisbad. This heat is then used for the swimming pools, the spa, underfloor heating, and even for heating the water used in the hotel. On the left, you can see a simplified diagram of the completion of this well. The second case study I wanted to show you is also a case study where the well in question was not originally drilled as a deep borehole heat exchanger, but for other purposes. The Weisbad well we saw earlier was drilled as an open-loop geothermal well. This second case study involves a well that was originally drilled as a gas well, and therefore for hydrocarbons, and was later considered as a potential closed-loop geothermal well. Where is this second case study located? It's in England, in the north of England. The rectangle shown in red on this map indicates the region where the site is located. This is a region where hydrocarbon exploration and development licenses were granted in the past. The area is therefore already known for energy production. Gas production in the area ended in 2019. The license expired, so to speak, in terms of time, but the operator's obligation to decommission these sites remains. Currently, no operator in the UK has reused hydrocarbon wells for geothermal purposes, but there's considerable discussion about it. The operator of this particular site realized that there was clearly geothermal potential. I'll explain why. One of the wells is extremely deep, reaching a depth of 3,000 meters. In 2024, this infrastructure was acquired by a new operator, a geothermal company. By acquiring the assets from the hydrocarbon operator, this geothermal operator also automatically took on all the obligations for the final abandonment of the field. So these final abandonment costs have not magically disappeared, but have instead been inherited by the new geothermal operator. An important aspect to consider is that the location where these wells are situated is also a national park, the New York Moors. So there are clearly restrictions on the operations that can be carried out there. My group and I have conducted several analyses of this particular case study and have published extensively on it. I have included in these slides an open access example of a recent publication we presented at Stanford. Let's take a closer look at the well that we focused on for this case study. The well is called Kirby Misperton 8. In these slides, we will simply refer to it as KM8. It is a vertical well, a little over 3,000 meters deep, drilled in 2013. At the time, it was still possible to consider hydraulic fracturing of gas wells. However, there were protests against fracking in 2017. Subsequently, the government here in the UK imposed a ban on fracking, and this happened in 2019. Since then, the well has remained as it was, drilled and cemented, with the casing inside the well. So it is a well that is already drilled and lined, stopping at 3,099 meters depth. And it was left in that condition without a hydraulic connection to the geofield present in the formation. For this reason, it is actually very suitable for conversion into a deep borehole heat exchanger. For this well, the geothermal operator who acquired it conducted some short-term plugging tests by inserting a concentric pipe into the well and letting water flow for several days. I would like to point out that the data from this pilot project has not been published. As far as I know, the operator currently has no intention of disclosing the detailed results, but we do have some information. We even visited the site with industrial colleagues, so we have some reference points. Based on this, we modeled the system independently. To give you an idea, this is the well area, shown in a photo taken from the Think Geoenergy organization that we referenced in our article. However, I wanted to point out that the well is located in a rural area, so finding a final use for the potential heat recovered from this well is already challenging. On a positive side, however, the area is considering building new homes, so even if there are no immediate uses for the recovered heat, there could be users in the short, medium, and long term. Anticipating what Michele will present in more detail, I will show you an example of a modeling approach for a case study of this type. As academics at the University of Glasgow, we used a code available in open access called OpenGeoSys, so anyone can use it. And we adapted the code specifically to model a deep hole exchange system. Without going into details of the modeling, I wanted to present the cases we analyzed. We asked ourselves the question, What changes if I place a concentric tube made of a different material inside the well? Specifically, we considered so-called vacuum-insulated tubing, or VIT, which is a thermally insulated tube with vacuum gaps. We also considered what you see here labeled HDPE, which stands for high-density polyethylene pipe. This is an inferior material compared to VIT, but it is also less expensive and is what the operator used for the pilot project. So HDPE performs worse than VIT. What does that mean? It means that in terms of thermal insulation, VIT insulates better. So when the fluid returns to the surface through this concentric tube, the tube provides more insulation when it is VIT than when it is HDPE. However, we did not only vary the material, we also varied the depth at which the pipe could be placed. The operator in the pilot project stopped at 2 kilometers. In the simulations, we asked, what if we went a little deeper? What if we tried to capture a little more temperature by reaching zones with a higher geothermal gradient at greater depth? So we modeled these cases and then looked at the evolution of the recovery temperature at the surface as a function of time, considering a period of up to 25 years. Why 25 years? Because typically this is the duration of a geothermal license, although there can be some variations. So, in the diagram on the left, you see the temperature of the fluid as a function of time in years, and on the right-hand vertical axis, you see the recovered thermal power. In other words, the kilowatts of thermal energy that are theoretically recovered from this well. In the diagram on the right, you see the temperature of the fluid as a function of depth, the temperature with the initial profile, and the temperature over time, at the beginning of the circulation, after 42 minutes, and also at the end after 25 years. Clearly, after 25 years, the system becomes cooler overall. By continuously circulating a cold surface fluid to recover heat, even simply through thermal conductivity, the surrounding rock is gradually cooled. We also attempted to perform sensitivity analyses on the nature of the circulating fluid. For example, pure water versus water with a small amount of salt. I would also like to point out that, in theory, supercritical CO2 can also be considered as a circulating fluid. However, we did not analyze this option in this particular case study. Up to this point, I have always referred to a clean circulating fluid. A simple example could be water, or perhaps water with the addition of a refrigerant, so that during the winter months at the surface, the fluid is not exposed to the risk of freezing. We also ran analyses to evaluate the effect of varying the internal tube material, specifically the VIT and HDPE we mentioned earlier. As expected, VIT shows superior performance. In addition, we must consider that HDPE is not designed to withstand very high pressures and temperatures. Therefore, at depths approaching 3 kilometers, that material should be excluded because it cannot withstand the pressure and temperature conditions at that depth. As we move toward concluding the results for this case study, we also examined the variation of the circulating fluid flow rate. The more fluid I inject into the system, the higher the flow rate of the fluid that can recover heat. However, increasing the flow rate also increases the velocity of the fluid, which decreases the residence time of the fluid inside the heat exchanger. In other words, the fluid has less time to absorb heat from the surrounding rock. So there is a trade-off between circulating the fluid too quickly and not circulating it quickly enough. In the end, the thermal power recovered is essentially the product of the flow rate and the temperature difference, combined with the thermal capacity of the fluid. This table, extracted from the article, provides a small summary showing how performance varies depending on the circulation flow rate. For example, 2 liters per second or 5 liters per second, and also on the injection temperature. For instance, I can re-inject a very cold fluid at 5 degrees Celsius or re-inject a warmer fluid. From this matrix, you can see the resulting thermal power. In this case, the highest value we obtained was 69.5 kilowatts of thermal power for re-injection at 5 degrees Celsius and a circulation rate of 2 liters per second. These results give us an order of magnitude for the heat recovery that can be expected from wells of this type. Finally, we also examined what might happen under a more realistic operating mode, where heat is used only for part of the year. For example, I may need heat during the 6 winter months, but not during the 6 summer months, allowing the well to rest. Clearly, the long-term sustainability of the well improves if the system is used seasonally rather than continuously. To conclude this section, we must consider that when repurposing old wells, meaning wells that have already been completed, the legal responsibility for the final abandonment of the infrastructure does not disappear. These abandonment costs remain. We must also consider that there are restrictions. The completion of an oil well is not necessarily the same as what a geothermal well would require. So sometimes drilling a new geothermal well may be the best solution. There is also the economic aspect to consider. Not only comparing geothermal options with other geothermal options, such as open-loop versus closed-loop systems, but also comparing them with other energy supply alternatives. Finally, in this particular case study, the well is located in a relatively isolated area, where there are currently few potential users for the recovered heat. Before finishing, I would like to present some innovative concepts that have been proposed by different groups. These involve the possibility of using closed-loop geothermal systems not only for heat production, but also for electricity generation. The diagrams I am showing you here are taken from patents filed in national and international patent systems. In the first concept, shown on the left, you see a design that envisions heat exchange within the well using a U-shaped configuration, combined with a split flow, so that the two separate flows have a greater opportunity to exchange heat with the surrounding warm environment. In addition, still referring to the diagram on the left, you can see that the well is filled with a material that has a higher thermal capacity to store heat, which can then be exchanged with the fluid circulating in the tube. On the right, you see a generator with a turbine placed directly at the bottom of the well, thus transforming the heat directly into electricity within the well. In the second example, you see a concept that we developed a few years ago, which we called artificial geyser. In this concept, water is injected deep into the annular portion of the well. The water is then allowed to pass in a vapor state through the downhole boiler, and the vapor rises naturally through the central tubing. On the right, you also see the possibility of improving the thermal properties of the material surrounding the deep borehole heat exchanger. Starting with the choice of cement used in the well, additives can be incorporated into the cement to improve its ability to exchange heat with the surrounding rock. The last point brings us back to the AGS, Advanced Geothermal Systems concept, which uses more advanced and complex geometries. An example of this type of system was recently completed in Germany at Geretsried. We are still waiting for official performance results. It appears that the performance may be somewhat lower than the initial expectations, which is not entirely surprising. On the left, you can see a diagram taken from a patent that was filed in 2010. So, in the history of geothermal geothermal energy, we often see ideas that reappear over time. It is interesting to observe how, after more than 15 years, this concept from 2010 has finally been implemented. With that, I will conclude my section and pass the presentation to my colleague Michele. Thank you. Good morning, everyone. After the excellent first part on closed-loop systems presented by Professor Falcone, in this second part, we will discuss the simulation, modeling, and therefore, indirectly, the optimization of these same systems.
Modelizzazione e quindi indirettamente ottimizzazione di questi stessi sistemi.
The first thing that becomes clear when observing closed-loop systems is that there is actually no strong need to simulate the rock formation from a hydraulic perspective in terms of flow through a porous medium. This is because what essentially happens is a heat exchange between the process fluid flowing inside the tubing of the closed-loop system, which may be coaxial or another configuration, and the rock formation immediately surrounding the tubing.
La zona di formazione rocciosa immediatamente circostante al tubo del nostro sistema closed loop.
For this reason, although nothing prevents you from using a three-dimensional grid system, such as CFD or finite element methods, to simulate the rock surrounding the pipe, it is usually preferable to use a system with cylindrical symmetry centered on the pipe axis. The important characteristics that we need to simulate are clearly the hydraulics of the process fluid flowing inside the closed-loop system and the heat exchange processes. In particular, heat transfer will mainly occur through conduction within the rock material in the immediate vicinity of the pipe, and through convection between the fluid and the internal wall of the system. Let us now look at the typical variables that must be considered at the modeling stage in order to effectively simulate our system. The primary output of interest is the outlet temperature. Secondarily, we are interested in the inlet pressure, which depends on a given inlet flow rate provided as an input value. In addition, we must consider a number of parameters related to the rock formation, such as density, thermal conductivity, heat capacity, and the radius of influence of the rock. Regarding heat exchange, we also consider the parameter Rext, the geothermal gradient between the surface temperature and the bottom hole temperature, and a heat transfer coefficient at the external surface of the rock. This is necessary because it is not feasible to simulate an infinitely large rock domain to represent the heat exchange process. Instead, we consider a cylindrical rock domain with sufficiently large dimensions, such that the temperature at its external boundary does not change significantly during the duration of the simulation. Typically, an external heat exchange coefficient is then defined between this cylindrical surface and the undisturbed surrounding environment. Finally, we must also define the geometric parameters of the system, such as the depth, pipe diameter, and the hydraulic parameters, including a roughness factor for the process fluid. For coaxial systems, such as the CLA system introduced earlier by Professor Falcone, there is an additional complexity. In this case, we must also simulate convection within the annulus, that is, the annular space between the pipes. In this region, the fluid flows downward while exchanging heat through convection within the annulus, and simultaneously receiving heat through conduction from the surrounding formation. This introduces additional requirements and capabilities that must be handled by the simulation software. Another very important aspect to simulate correctly is what is called the wall of the rock formation. which also includes all the layers of steel and concrete that are interposed between the rock and the process fluid. As you can see, and as has already been introduced earlier, the system is rather complex. There are layers of different kinds, including insulating layers, certainly in a coaxial system, but also near the surface for both coaxial and U-shaped systems. In these zones, there is a need to keep the rising fluid sufficiently hot and prevent it from losing heat through exchange with the formation layers that are closer to the surface. The simulation of the wall, meaning the sequence of solid layers, rock, steel, concrete, insulation, and any other materials that lie between the external surface of our simulation model and the fluid, is therefore particularly important for accurately representing the conduction and convection processes. A brief overview again on insulators. This part has already been covered in the first part of the presentation. If we focus only on vacuum insulated tubing or VIT systems, the modeling generally involves simulating a steel sandwich structure consisting of an external layer and an internal layer. Between these two layers, there is a vacuum gap, which is clearly difficult to simulate numerically as a true vacuum. Instead, it is common to use air at very low pressure, which should reasonably approximate the real case, since achieving a perfect vacuum is not easy in practice. For other materials, there are no particular difficulties. It is simply a matter of introducing thermal properties, such as thermal capacity, conductivity, and density for plastics, high-quality cements, or even insulating cements that can be used in the system. The final ingredient necessary for the simulation is, of course, the most accurate possible modeling of the process fluid. This table provides an overview of the fluids most commonly used in closed-loop systems. These range from pure water to more complex mixtures based on nanofluids, which are liquid mixtures containing metallic compounds that can, theoretically, increase the thermal conductivity of the fluid. There are also liquid-solid mixtures, or slurries, in which suspended particles can change phase from solid to liquid, absorbing heat and thus optimizing the transport of energy to the surface. To simulate these fluids properly, a PVT, or pressure volume temperature simulator, is required. This simulator must be sufficiently accurate and must incorporate detailed equations of state or correlations to manage these fluids over the temperature and pressure ranges typical of the systems we want to simulate. Some of the fluids listed at the bottom of the table require additional modeling complexity. However, these are not insurmountable obstacles. Now, let's move on to the substance of the simulation itself, rather than simply the parameters used. The first important point to underline is that simulations are normally carried out as stationary simulations, assuming equilibrium conditions from the start. This is what you see in the graphs below as a dashed line, which represents the equilibrium temperature of a closed-loop system that has been operating since the beginning under perfect thermal equilibrium between the formation and the surface system. In reality, however, what normally happens is that there is a long thermal transient. The rock formation initially has a certain temperature that differs from the temperature of the injected process fluid. The thermal inertia of the surrounding rock is quite high because heat exchange occurs mainly through conduction. As a result, what we observe is what you see in the blue line in the left graph and the red line in the right graph. The two graphs differ only in the time scale. We observe a very long transient phase, which can last several years, during which the outlet temperature gradually decreases as the process fluid and the surrounding rock formation move toward thermal equilibrium. This is an important parameter to keep in mind. Stationary simulations that assume equilibrium from the beginning are generally conservative with respect to outlet temperature predictions. In reality, the outlet temperatures observed in operation are often higher than those predicted by stationary simulations. The typical pressure, temperature, and velocity trends are qualitatively illustrated in this slide. Here you can see what happens in a typical U-shaped configuration. The fluid is injected from the surface, represented by the blue line. It heats up at depth in the horizontal section, the green line, and is then brought back to the surface. In this particular example, we do not include any thermal insulation in the U-shaped configuration. However, we can clearly see that the outlet temperature in the first graph is significantly higher than the inlet temperature. Pressures and velocities are constant because the diameter of the tube is constant. What happens instead in a coaxial system is that, over time, there is a significant temperature gain between injection and production. We also observe a pressure differential at the surface that must be overcome due to friction losses, especially in the annular section. We will look at this in more detail shortly. In addition, the velocities in the annular section and in the central tubing are significantly different. Depending on the diameters, there is therefore the possibility of optimizing them. Here we see a qualitative comparison between the coaxial systems. In this example, we consider a well with the same depth of 2,600 meters, with 7-inch diameter tubing, used both for the internal part of the coaxial system and for the pipe section considered in the U-shaped configuration. It can be seen that coaxial systems usually perform slightly worse in terms of outlet temperature than U-shaped systems for the same flow rate. For coaxial systems, the outlet temperature increases as the diameter of the coaxial system increases, particularly the annular section, because this increases the heat exchange surface area. For U-shaped systems, the outlet temperature increases as the length of the horizontal section increases, because this extends the heat exchange section. From this perspective, it might seem advantageous to simply make wider and longer pipes in order to obtain higher temperatures. In reality, this is not exactly the same case, because there is a balance between convection and conduction, as illustrated in the figure on the left and represented numerically in the figure on the right. Essentially, when we increase the flow rate, the resulting effect can actually be a lower produced temperature, because conduction is much less efficient at transporting heat from the outer rock layers to the pipe than convection is at extracting heat. What happens, therefore, is that increasing the flow rate causes convection to cool the surrounding rock formation. You can see this effect in the difference between the red line, the red plot, and the blue plot in the graph on the right. This is therefore a very important parameter to consider when optimizing these systems. Another related issue is the difficulty and limitation associated with drilling. We cannot drill wells with very large diameters at great depths, because for structural stability and pressure resistance, wells must be constructed with a telescopic design. This means that as we go deeper, the diameter of the pipe must decrease. Another important factor to emphasize is friction losses. For U-shaped configurations, shown in the graph on the left, the behavior is similar to that of any pipe. As the hydraulic diameter decreases, the friction losses increase significantly, while larger diameters result in lower friction losses. For coaxial systems, however, if we look at the total pressure losses, that is, the sum of those in the annular section and in the tubing, we observe that there is an optimal point. If the tubing diameter is too small, the losses in the tubing become very high. We are on the left side of the graph. If the tubing diameter is too large, the annular section becomes restricted, which again leads to high losses in the annular region. Therefore, there is an optimum somewhere in the middle. These friction losses are directly related to the power consumption of the surface pumps, so identifying this optimum is very important during the design phase. This sensitivity analysis is therefore particularly important. I will now move quickly to another consideration: whether in U-shaped configurations it is more advantageous to construct a pipe with a very long horizontal section or instead a deeper vertical section. Based on everything we have discussed so far, the system response is nonlinear, especially at high flow rates, and therefore modeling becomes fundamental. It is necessary to perform a sensitivity analysis, possibly assuming the same total drilled distance, in order to determine which configuration produces the best combination of temperatures. It should also be considered that there is a technical and economic optimization problem. The deeper the well, the higher the drilling costs. At the same time, long horizontal drilling over long distances, especially when it is truly horizontal, also involves significant costs. Therefore, the parameters involved in system optimization are complex. The numerical simulations are extremely helpful in addressing this problem. Finally, a very brief overview of alternating systems. This was already discussed by Professor Falcone in the first part of the presentation. It is normally possible to introduce a control logic into simulation systems that allows the modeling of alternating wells. Here we see a system of 3 wells, only one of which is operating, while the other 2 are in the warm-up phase. By appropriately calibrating the temperature thresholds and starting from initial transient conditions, as you can see on the left, the first well, the green one, is activated first. When the first well cools down, the second well is activated, and the first one is placed on standby. Subsequently, the system switches between the second and third wells until a stationary condition is reached. At this point, the 3 wells, with minimal user-defined temperature fluctuations, are able to supply the surface plant heat exchanger with an acceptable flow rate at a more or less consistent temperature, with only small variations caused by the switching cycles. The issue of seasonality was also discussed in the first part of the presentation. In this case, the simulation considers 2 wells that remain shut down for a certain period. Here, the modeling becomes slightly more complex. The only real difficulty is the need to extend the simulation time in order to reach the stationary phase. This is because we are now considering timescales of years, whereas in the previous scheme, we were considering shorter timescales, such as days or weeks. Well, I am now concluding my presentation. One final evaluation that can be performed at the modeling level, which is very useful, is to determine the total lifetime of the closed-loop system, and also to evaluate the effective radius of influence of the well within the rock formation. In other words, we want to determine how far apart 2 adjacent closed-loop wells should be drilled, so that they do not interfere with each other, and so that each well has a sufficient volume of surrounding rock from which to extract heat. To evaluate this, we can simply run 2 simulations. The first corresponds to the initial conditions of the undisturbed rock, with the natural geothermal gradient. The second simulation assumes a temperature depletion in the rock formation. This is illustrated in the graph at the top right. The red line represents the initial temperature profile. The yellow-orange line represents the same temperature profile after the rock has been cooled by about 10 degrees Celsius. What we can verify is whether, under these 2 conditions, the heat exchanger is still able to provide a relatively constant temperature difference, possibly by slightly adjusting the reinjection temperature into the system. In this specific example, this is indeed feasible. In the figure at the top right, the area of the triangle represents the thermal energy that has been removed from the rock formation. Meanwhile, the temperature difference multiplied by the flow rate provides an estimate of the thermal energy extracted from the system on a daily basis. By
Facendo il rapporto
calculating the
posso
ratio
determinare
between
quant'è la
these two
durata di vita
values,
dell'impianto
we
prima
can
di
estimate
ottenere questo
the operational
raffreddamento della
lifespan
roccia.
of the
In questo
system
esempio si vede
before
che il raffreddamento di
significant
10 gradi
cooling of the
sulle
rock
condizioni del
occurs.
pozzo
In this
precedente,
example,
intorno
a 10 degrees
5.000 metri,
Celsius cooling of the
consentono un
formation
55, una
for a
cinquantina d'anni
well
di vita
approximately
operativa
3,000 meters deep
portata
corresponds to an
costante e quindi
operating life of
flusso di
about
energia costante in
55
tutto il
years,
sistema.
assuming a
Notate
constant
che
flow
nella
rate
slide
and therefore a
precedente
constant
abbiamo
heat
assunto un
extraction rate.
raggio di
It is
50
worth
metri
noting
per
that
la
in the
zona di
previous
simulazione
slide,
e
we
vediamo che
assumed a
questa è
50-meter
effettivamente più che
radius for
adatta
the simulation
a
domain,
50 anni
and
di
we
vita
can see that this
operativa
is
del
more
nostro
than
sistema, che
sufficient,
sono
given that the
sicuramente
system's
superiori alla vita
operating life is
dell'impianto.
around 50
Quindi
years,
la
which is
conclusione è che
consistent
nella
with the
nostra
expected lifetime
formazione
of the
rocciosa abbiamo
installation. The
moltissima
conclusion
energia
is therefore
e siamo
that there is
assolutamente
a
in
large
grado di
amount of thermal
sostenere
energy
questa
available in the
installazione
rock formation,
geotermica
and that
closed loop
closed loop
per
geothermal
tempi
extraction
lunghi,
can be sustained for long
chiaramente
periods of
aumentando
time.
la
Of
richiesta di
course,
energia posso
if the energy
aumentare
demand
il raggio di
increases,
azione di
the
efficacia e
effective
questo mi darà
radius of
anche la distanza
influence will also
critica a
increase.
cui posso
This
andare
value
a
also
portare
provides an
complessivi.
indication of the
In
typical
questo caso, per
spacing
esempio, con
between
50
wells.
metri
In
il
this
sistema di
example,
closed loop che
with
devo
an
inserire
influence
non
radius of
saranno
about
più
50 meters,
vicini
the
di
closed
100,
loop
di
systems should
200
be
metri
placed
tra loro,
at
in
least
modo da
100 to 200 meters
separarli.
apart,
Quindi,
allowing for a
concludendo,
reasonable safety
la
margin.
parte
So, in
modellistica di questi
conclusion, the
sistemi è
modeling of these
fondamentale
systems is
sia per
fundamental, both for
questioni di
design
design
and
che
system
di
sizing, as
dimensionamento
we have
e
just seen.
quantità, come abbiamo appena
It is
visto, e
especially
soprattutto per
important for performing
tutta
the
una serie
various
di sensitività
sensitivity
che devono
analyses
essere
required
fatte,
to
che
address
consentono
the
di superare
nonlinear
non
behavior of
linearità
the
del
system,
sistema
which results from the
intrinseche
coupling between
allo
hydraulic
scoppiamento tra
processes
idraulica,
and heat
sistema
transfer
geotermico per
through
conduzione e
conduction and
convezione,
convection.
e consentono di
Modeling
superare le
therefore allows
oscillazioni
us to provide reliable and acceptable performance
ovviamente
predictions
valide e
for these
accettabili
geothermal
per
systems.
il nostro
And with
sistema.
that, I conclude
Con
my
questo concludo.
presentation. Thank you
Grazie
very
mille,
much, Michele.
Michele.
I'll now bring Gioia
Richiamo
back in.
anche
She's been waiting in the
Gioia, che
waiting
nel
room in the
frattempo
meantime,
era in sala
so that she
d'attesa
can help
per
answer the questions
essere
that have
pronta a
arrived.
rispondere alle
I'll
domande che
also
nel
remove the
frattempo sono
slides so we
arrivate.
can split the screen and be ready to
Tolgo le
address all the
slide
questions.
in modo tale che possiamo dividerci lo schermo ed essere pronti a gestire le domande che abbiamo visto scorrere.
I
Io
will
adesso ve
read
le
them and
pongo
suggest that each of
e
you respond
propongo,
depending
diciamo, a
on the
ciascuno di
timing of the
voi
questions
di
during your
rispondere sulla
presentations
base
and the topic
dell'argomento in cui
you
sono arrivate
discussed.
le domande
Of
durante le vostre
course, both of
presentazioni
you are free to
e
intervene
dell'argomento
even
che
on
avete
questions that
trattato, ma
appear to be
chiaramente
directed to the
ciascuno di
other,
voi è
given
libero
your
di
shared
intervenire
expertise.
anche su domande che apparentemente sono rivolte all'altro, visto le competenze di entrambi.
I'll start with a
Parto
question
quindi con
for
una
Gioia,
domanda
which is
per
also
Gioia,
the
che è
first one that
anche la
arrived
prima che è
from Frank.
arrivata da Frank,
He
che
asks,
chiedeva se
for the
con la
CXA
configurazione
configuration,
fissa
how can we ensure the thermal
come si
insulation of the
faccia a
pipe
garantire
in order to
l'isolamento
optimize the
termico del
heat
tubo per
received
ottimizzare il
from the
calore
subsoil?
ricevuto dal sottosuolo.
Thank you,
Grazie Alessandro,
Alessandro, and
grazie
thank you,
Frank
Frank,
per la
for the
domanda.
question.
Come abbiamo
As we have
visto,
seen, there are
ci sono
several
queste
material
possibilità
choices
di
available.
scelte di materiali. Io ho
I
parlato
mentioned
dei commissori
vacuum
speciali
insulated tubing,
dell'HDPE,
VIT, and
che hanno delle proprietà
HDPE, which
termiche
have different
diverse.
thermal properties.
L'isolamento totale al
Achieving
100% no,
100%
forse
perfect
raggiungibile, ma ci
insulation may
sono
not be
materiali
possible, but
superiori
some
rispetto agli
materials
altri.
perform better than
E hai
others.
visto che anche
Michele
Michele
also
ha
discussed
aggiunto
in
che
more
abbiamo
detail
delle
how the
possibilità,
required
si può
vacuum
o meno
insulation can be
aggiungere il
achieved,
vacuum
in addition to the
e
choice of
anche al
materials
di là della
both
scelta
for
del
the central
materiale tubo
tube and for the
centrale, la scelta
materials
di
surrounding the
materiale
casing.
all'intorno del casing.
Great,
Benissimo,
thank
ti
you.
ringrazio.
And Michele, I'd say there's
Michele,
no
direi
need to
che
add anything more.
non c'è motivo di
Instead,
aggiungere nulla.
I'll ask you another
Ti
question,
faccio
trying to
invece un'altra
alternate
domanda, per
between
cui
you
cerco di
two,
alternarle,
even if
anche
I'm
se
not
adesso non
strictly
rispetto
following the
l'ordine con
order
cui
in
le
which the
domande sono
questions came
arrivate.
in.
E
This
questa volta
time,
è
Lorenzo
Lorenzo che chiede
asks
se a
whether
livello numerico
numerically
la
simulating
simulazione
a
di un pozzo
coaxial well
coassale sia più
is more
onerosa
demanding than
di quella di un
simulating a
sistema
U-shaped
e in
system, and
caso
if so,
di quanto,
whether the
cioè se
additional
sia
computational
quantificabile
cost
la
can be
maggior capacità di
quantified.
calcolo richiesta.
Thank you
Grazie
for the
Lorenzo
question,
per questa
Lorenzo. In
domanda
principle, it does introduce
in
an
linea di
additional
principio
complication, but
diciamo,
if
si
the
introduce una
system
complicazione
geometry
aggiuntiva,
remains
però
relatively
se
simple,
il sistema
especially
ha
when
una
assuming
geometria
radial
francamente
cylindrical
semplice,
symmetry,
faccio ancora
the additional
riferimento alla
effort is
struttura
not
di costruzione
particularly
dell'elettrodo
demanding.
radiale,
The central
ma
tubing can be treated as a
l'introduzione
sink
alla fine
or
non è
source
poi così
with respect to the
complicato.
outer
non è
tube,
così onerosa
and
perché
convection is already
il tubo in
simulated
centrale
in the
viene
model
trattato
when
come
predicting the
un
heat
sink,
exchange
una
between the
cesta appunto
pipe and the
per quanto
surrounding
riguarda poi
formation.
il tubo più esterno. E la convezione comunque viene già comunque simulata nel nostro modello quando dobbiamo prevedere lo scambio termico tra il mio tubo e la
So,
formazione.
essentially,
Quindi,
we are
sto
just
solo
adding
aggiungendo un
additional
ulteriore
calculations using the
calcolo,
same
però riguarda anche
methodology
la
already
stessa
present in the base
metodologia
simulation,
che è già
and
contenuta
therefore,
nella
the
simulazione
additional
di base.
computational
Quindi non è
burden is
particolarmente
not very significant. I understand, thank you. Let's move on to another question for Gioia, again from Frank. He asks whether there are wells where multiple tubes are used to optimize production.
Più tubi per ottimizzare la produzione.
Yes, Frank, we actually saw an example of this when I was discussing concepts proposed for power generation systems. In that example, the pipe splits into two branches at depth and remains as a double pipe configuration until the flow recombines before the final exit. So, in principle, the concept exists, but we have not yet seen it implemented in real systems. At the moment, these ideas mainly appear in patents and research articles. The concept is elegant because it would increase the heat exchange surface between the fluid and the surrounding formation. So, in principle, yes, but as far as I know, it hasn't been implemented yet. However, there are also practical constraints, including additional costs and the limited space available inside the well. As Michele mentioned earlier, the deeper the well, the smaller the diameter becomes, which further limits the possibility of splitting the tubing. In AGS-type systems, such as the EVOR concept, multiple branches are actually used, but that is a different type of system, not a single deep borehole exchanger. So, in a single well, the available space for this kind of branching is quite limited. I can add a small detail. We have tried to simulate this type of configuration in a coaxial system. For example, by installing two tubings. The results so far appear to be similar to those obtained with a single tubing coaxial system. However, we have only performed a limited number of simulations, so we are still investigating whether there is room for improvement.
Quanto sia grande il margine di miglioramento, però diciamo che lo stiamo investigando. Da quel punto di vista lì sì.
Let me now ask Michele another question from Andrea, who asks whether it is computationally possible to simulate natural or forced convection outside closed-loop systems. Thank you, Andrea. That is a very important question. In principle, yes, it is possible. However, doing so would require simulating the rock formation as a porous medium, including fluid flow within the formation itself. At that point, the problem becomes significantly more complex. It is no longer just a matter of heat exchange, but also of fluid flow through the porous medium.
Un livello di modellistica molto più sofisticato di quello che abbiamo fatto per questo tipo di sistemi, cioè qui a questo punto non c'entra più soltanto lo scambio termico, ma andiamo proprio a coinvolgere il flusso in mezzo poroso.
We would need to consider whether the convection is natural or forced, what mechanisms are causing it, and whether there are external wells or other flow sources influencing the system. So it's certainly possible, but it is much more difficult and requires a much more advanced level of modeling. Thank you. Another question for Gioia, this time from Biagio, concerns the long-term deposition of residues inside the pipe. He asks whether VIT or HDPE performs better in this regard. Biagio, if you're referring to flow assurance type deposits, we must remember that the fluid circulating in the closed-loop system is a clean fluid selected at the surface, so as not to have a difficult or problematic chemical composition. It is not a natural geofluid, which could produce salts or mineral deposits. So these types of issues are generally much less problematic in closed-loop systems. If your question refers instead to pressure drops caused by different configurations, then yes, that could influence flow behavior. But again, the advantage of a closed-loop system is precisely that we avoid the complications associated with natural reservoir fluids. Thank you.
C'è una
There is another question
domanda
from
ulteriore
Paolo, if I'm not mistaken. I
viene
think
da
Michele
Paolo, se
answered
non
it
ho
somehow,
visto
but I'd
male,
like you
che
to
chiedeva se
elaborate
ci
on this
sia,
answer.
e credo che
Whether there
Michele in
is a
qualche modo
minimum
abbia
spacing
risposto,
or
ma
radius of
ti chiedo di
influence
approfondire
between
questa
wells,
risposta.
depending on
Se
rock
ci sia
properties such
una
as porosity.
distanza minima o un raggio di influenza tra due pozzi in funzione della formazione rocciosa, della porosità o di...
Yes, absolutely.
Assolutamente
That was
sì,
precisely
erano
the
proprio il
content of the
contenuto delle
last
ultime
2
due
slides.
slide.
First of all,
Grazie
thank you,
Paolo per
Paolo, for the
la domanda. Sì.
question. Yes,
Non è
however,
semplice
it
dare
is
una risposta
difficult to give
univoca,
a
dire
single
metti su questo
universal
5 metri
answer,
di
such as
distanza l'uno
saying that
dall'altro è
wells
così
should
puro.
always be placed
Dipende da tante
100
cose,
meters
dipende da
apart.
che tipo di
It
formazione
depends on
abbiamo, da tipo
several
di gradient
factors,
termico, ma
the type of
soprattutto dalla
formation,
perché io voglio
the
farci capire.
geothermal gradient, and above all, the
A
flow rate
portate più alte,
circulating in
come
the
si è
system.
visto durante la
At higher
presentazione,
flow rates, the
il
fluid
nostro
cools the
fluido
formation more quickly,
raffredderà
so the
la
thermal
formazione,
radius of
quindi
influence
questo raggio
becomes
di influenza
larger, and greater
termico sarà
distances
più
between
basso in
wells
condizioni
may be
reali, quindi
required.
ci vorranno distanze più grandi.
As an
Posso
order of
dire che l'ordine
magnitude,
di
we are
grandezza
typically
le
talking
dimensioni
about
di Mooc,
tens of
questo
meters,
sì,
not
penso che
hundreds.
arriveremo
I
magari
don't
a
think we'll
5
ever get to
metri,
hundreds of meters,
insomma,
unless for
non
very
credo
high
che si
flow
riesca
rates,
con
but in
portate,
this case,
a sto
hydraulics
punto
can't handle
l'idraulica non
any
regge
more,
più e
and
quindi non riesco
therefore
a
I
gettare più
can't
di una
inject that
portata,
much
però
flow. But again,
ecco,
that's the
l'ordine di
order of
grandezza è
magnitude.
quello.
In
Trovare poi
practice,
effettivamente
determining the
l'ottima,
optimal
quello che
spacing
bisogna cercare,
usually
perché la risposta
requires
come si fa
numerical
non è lineare,
simulation because the
non si può
system
fare
response is
calcolo a tavolino.
nonlinear, so you can't do a straight calculation on that. Yes.
Sì,
So forgive me,
perdonami,
I'll take this
approfitto per fare
opportunity to
anch'io una
ask a
domanda
question about the last point you
sulla
made.
questa
So the
ultimo inciso che hai
optimization is
fatto.
always
Quindi
based on
l'ottimizzazione comunque è
simulation,
sempre
so it is a
basata su
numerical
simulazione,
optimization. There
quindi è
are no
un'ottimizzazione numerica, non
Yes,
ci
yes, for many
sono,
Per
aspects,
diciamo...
tanti
some
aspetti
things
sì,
maybe not. For
alcune
example,
cose
the
magari no,
friction losses
per
can
esempio
also
per
be
l'idraulico
calculated in
possono
another
calcolare
way
in
without
altro modo
necessarily
senza dover
having to
ricorrere per forza a una
resort to a
simulazione.
simulation.
Però
But let's
diciamo
say that the
che l'interazione
interaction, thermal-hydraulic
termodinamica, chiamiamola così,
interaction
tra
between the
la
thermal
parte
conduction,
termica,
convection,
conduzione,
and then the
convezione
flow
e
in the
poi il
pipe
flusso nel
needs to be
tubo,
simulated.
quella da
As I see it,
simulare
having it
diciamo a
theoretically
tavolino,
calculated
da
is rather
calcolare a tavolino
difficult.
la vedo piuttosto
Sì.
difficile, ecco.
Thank you.
Grazie.
I don't
Poi
know,
se
Gioia,
volevi
if you
aggiungere
wanted to add anything to the
qualcosa
question
sulla
Michele
domanda
just answered,
a cui ha appena
namely the one
risposto
regarding
Michele,
the
cioè
distance
quella
between the
relativa alla
wells.
distanza tra i
I
pozzi.
can confirm that.
Se...
If we're
No,
talking about the
confermo che appunto
tens
stiamo
of
parlando
meters,
della decina di
we've
metri,
seen
noi
our
abbiamo visto anche
simulations no
simulazioni
more
molto
than 30 to
dai
60
30 a
meters
60
of
metri di
influence.
influenza, poi dipende
Then
anche
it
da
also depends on
quanto
how
di
long the
Saipem,
system
questo
lasts.
conferma un
And
pochino
this
anche i
also
limiti
confirms the
che
limits a little.
questo raggio
That
ci dice
is,
anche
this
che
radius also tells
è
us
il
what
volume
the
massimo di
maximum
roccia
volume
che
of
può
rock
andare a
is
contribuire
that
a
can
ottenere
contribute to the
comunque il
heat produced by the well.
Certo.
Another question
Questa
from Frank
sempre da
asks,
parte di
what
Frank,
conditions are
la
necessary to
pongo ad
obtain an
entrambi,
outlet temperature of around 15
riguarda
degrees Celsius in a closed
diciamo,
loop system?
quali
And
condizioni
what
bisogna
the
trovare per
theoretical
avere una
temperature of the
temperatura
surrounding rock that
riuscita
heats
attorno
the
ai
injected
15
water
gradi
might
nel
need to
sistema
be?
closed loop.
Michele, do
E
you
quello
want to
che
start?
chiede nello specifico è quale potrebbe teoricamente essere la temperatura della roccia che riscalda l'acqua iniettata.
I'll go, yes. That's a difficult
Vado io?
question. Thank you,
No.
Frank. However, it's a difficult
Domanda
question
difficile,
because
grazie
15 degrees
Frank, comunque è
Celsius
una
or
domanda
59
difficile
degrees
perché
Fahrenheit on the
ora
surface
15
isn't
gradi da
much,
ottenere
meaning
soprattutto
you
non
can still
sono
increase the
insomma
outlet temperature without any problems, especially if you
salire in
dig deep.
temperatura senza
There are several
problemi,
parameters
soprattutto se
involved.
io scavo in
Lower
profondità.
flow rates generally produce
Allora, qui i
higher
parametri
outlet
sono
temperatures
portate
because the
basse mi
fluid
daranno
spends more
temperature più
time
alte,
absorbing
questo
heat.
sicuramente. Se scavo in
Also, the
profondità
deeper the
ottengo
well, the
temperature
higher
più
the
alte,
temperature, and the
qui il
local
gradiente
geothermal gradient
geotermico
plays
è
a major role.
importante e più ottengo a
These, in
temperature
my
più
opinion,
alte.
are the main parameters.
Questi,
Now,
secondo me, sono i
Gioia,
parametri
maybe you'll confirm my
principali,
point,
poi
but let's just say it from a broad view.
magari mi
There's
conferma, però
also the
diciamo
fluid issue,
così
what
a
I can
vago. C'è
consider.
anche un discorso di
Maybe if I
fluido
use
che
water
posso
or if I use
considerare,
something
magari
else.
se uso
Well,
acqua
then the
o
energy, the
qualcos'altro.
heat I'll extract will
Poi
be more or
l'energia
less the
poi il calore che
same.
andrò a
But
estrarre
let's say,
sarà
if we're
probabilmente quello.
just
Poi
talking
diciamo,
about
se parliamo di
temperature, I can increase
temperatura,
the temperature
posso salire in
perhaps at the
temperatura, magari
expense of
scappi
something
poco
else.
di
But
qualche
saying, for
grado.
example,
Però
that to get to 15 degrees
diciamo,
Celsius or 59
dire
degrees Fahrenheit, I have to
avere
dig
15 gradi devo
500 meters
scavare
or
500
5 inches deep.
metri,
Well,
5
I
pollici,
don't have a
questo
clear
non
answer
ce l'ho
to
una
this. I can
risposta
only tell
così
you
univoca.
What
Posso solo
the
dire quali
important
sono i parametri
parameters to consider are.
da considerare.
In the example we discussed
Io
from
posso
Switzerland,
nell'esempio
the
che abbiamo
target
proposto
temperature was
del
about
caso
15 degrees Celsius
Bogliolo
at the
in
wellhead.
Svizzera,
In that
lì
case, the
parlavamo
well
proprio di
depth
una
was
temperatura di
about
ancora più gradi e in quel
1,213
caso
meters,
appunto
and the
è meglio
temperature at
sempre
that depth
semplicemente più
was roughly 45 degrees Celsius. And then, as Michele was saying, it also depends on the site, on the geothermal gradient on site, which can vary depending on the type of completion, on the type of system. But as a rule of thumb, 15 degrees Celsius at wellhead with a bottom hole temperature of about 45 to 50 degrees Celsius can reasonably produce around 15 degrees Celsius at the surface, depending on the configuration. I'd add that we're still talking about deep geothermal, meaning it's not a shallow geothermal where maybe I have 15 degrees Celsius because I'm building a different type of system. In other words, in these cases, we're still talking about depths of at least 1,000 meters. So we're going to encounter temperatures in rock formations, as Professor Falcone was saying, and higher as we go deeper. Another question that came in again from Frank concerns the fact that after 25 years of operation, it's necessary to abandon the wells due to the temperature variations induced in the rock. Well, here, the years we used, the 25 and 30 years you saw in Michele's and my posts, corresponds to the typical length of an operating license. However, it does not mean that the system must be abandoned after 25 years. And I'd also say that in terms of the integrity of the well infrastructure, the wells can sustain longer durations. Then there's also the issue of optimizing use. As Michele and I have shown together, seasonal use, alternating use, can extend the thermal sustainability of the system. So don't take it as an official cutoff. It's what's generally used in the analyses. I absolutely confirm what Gioia said, that all these calculations are calibrated for the life of the system, that is, the surface. Then again, much heat is available underground. It can be extracted. It's slow to extract, but it exists, so it's not impossible. In fact, it's very possible to achieve a lifespan of decades. Clearly, the questions to ask are about the survival and wear of the surface system. Of course. There was a question from Paolo that I struggled to find because it related to a specific moment in the presentation and was split between several speakers. However, it essentially concerns the effect of increasing fluid velocity and therefore a greater flow rate slows conduction and then convection due to the fact that heat exchange takes longer. It's a bit like the law of solubility, which states that too much, too fast means not having time to mix two substances. This, in short, is the question. Can I start? Going faster means cooling the formation and therefore exiting with slightly lower temperatures. Going slower, however, also means giving it more time to extract heat. And then normally going slower means using a slightly lower flow rate. So, in the end, there's this issue here too. But let's say we see this phenomenon very well with simulations by running the simulations, and there are optimal speeds, I believe. For coaxial systems, typical optimal velocities are roughly 0.2 to 0.5 meters per second for the descending and ascending flows. However, these are only approximate values, regardless of the hydraulic diameters. We are more or less in that range to obtain the maximum temperature in terms of heat extraction. Then again, this is just a semi-empirical consideration. Let's look at it that way. Well, I don't know if Gioia wants to add any other considerations on this. I can only say this here as a simulation worker. I mean, as we were saying before, we have to take into account the fact that the heat flux is the product of the flow rate, the temperature difference, and the specific heat capacity of the fluid. So it is not the flow rate, that is, the speed, alone that determines how much heat flux is recovered. So there's an optimization issue, as Michele was saying, which he addressed on a case-by-case basis. And don't forget what Michele was saying about friction. When we circulate in the system at high speed, the pressure loss due to friction increases, and ultimately, there can be a counterproductive effect. The greater the pressure loss, the more I have to circulate the fluid with pumps, and the pumps have a parasitic load. That is, I have to expend electricity.
Cioè devo spendere
Hanno un
elettricità.
consumo.
There's a balance even with the
anche
pressure
con i
losses.
pezzi di pressione.
Yes, all of this is absolutely
Assolutamente
true.
verissimo.
In
Nel
other
senso, poi
words,
alla
in
fine il
the
nostro
end,
scopo
our
è
goal is to
estrarre
achieve
l'energia
net
netta. Se
energy.
io ho tutto
If
quello che
all I
riesco a
can
produrre
produce must
e
be
me lo devo
depleted
mangiare
because the
perché le pompe
pumps
assorbono
absorb
quasi
almost
tutta la
all the
potenza che ho
power I've
estratto
extracted,
e non
it's
vale-
not
non
worth
valeva
it.
la pena
It
cominciare
wasn't worth
il
starting the
progetto di
project.
explorazione.
That's an
Ottima
excellent point.
considerazione.
There's
C'è anche
also
una
a service question
domanda,
from
diciamo,
Ilaria,
di
who says she
servizio
can't
da parte di
access
Ilaria
the
che dice che
slides
non
and
riesce ad
tests.
accedere
I would like to
alle
remind everyone that
slide
these
e
are
ai
associated
test
with all the
che
lessons, which
ricordo a
are
tutti sono
instead delivered
associati a
in
tutte le
open mode, including
lezioni
on YouTube.
che vengono invece
But those of you
erogate
who
in
aren't already
modalità
enrolled in the
aperta
course
e
on the
su
Mooc
YouTube,
Uniurb
ma
platform
chi
can
di voi non
always do
fosse già
so.
iscritto
And there you'll
al
find
corso
all the
online
slides as well
sulla
as the
piattaforma di
consolidation
Uniurb può
tests.
sempre farlo e lì ritrova tutte le slide che vengono presentate e quindi scaricabili e consultabili e dei test di consolidamento.
The
Il
issue
problema che
Ilaria reports is
segnala
related to an
Ilaria è
update to the
legato
authentication system that's
all'aggiornamento
still in
del sistema di
progress, so I can't
autenticazione
give you
che è ancora in
definitive instructions
corso
on
e
how to
quindi
use
non
the
vi
new
sto dando le
authentication system until
istruzioni
the update is
definitive su
complete.
come utilizzare il nuovo sistema di autenticazione in attesa che sia terminato l'aggiornamento.
This
Questo
information
inciso
obviously does
ovviamente
not apply to those who will be
è
watching
di
this lesson on
interesse
demand
per chi
later.
seguirà questa
We're
lezione
live, so any questions are
in
welcome,
diretta e
including ones
quindi
like
ogni
this
domanda è
that simply
lecita,
concern technical
compresa
aspects of the
quella
course.
come questa che riguarda semplicemente aspetti tecnici nell'erogazione del corso.
At the
Non ci
moment,
sono
there are
altre
no further
domande, ci
questions,
sono
but we have
apprezzamenti e
received many
ringraziamenti
messages of
per
appreciation for the
la
clarity and
completezza
thoroughness
anche
of
delle
the
vostre
answers.
risposte, la
So I would like to
generosità
thank you both
nel
very much
cogliere
for your
tutte le domande che sono
availability
state
and for this
poste.
excellent
Io
lesson. Gioia,
non posso che
Michele, thank you
ringraziarvi
very much.
moltissimo per la chiarezza e la disponibilità e complimentarmi per la lezione. Gioia, Michele.
Thank you.
Grazie a voi, grazie tante. Grazie.
And thank
Grazie
you,
come
as
sempre
always,
a
to
tutte e
all
a
of you
tutti
for
per aver animato
participating
il
and
dibattito.
contributing to the discussion.